Hello everyone, we are on Unit 3 and this unit, here is the front of the video packet, is about implicit differentiation, which you'll learn what that is, and these things called related rate problems. Okay, so that's what Unit 3 is about. The first lesson from Unit 3, video 3-1, that lesson, is to be watched Wednesday 11/2, November 2nd. And for homework, it's only one problem. It's page 3, number 6. Okay, so guys, there is this thing called L'Hopital's rule, okay? Now, you could read, I encourage you to read through this first page. This is just something that I borrowed from the internet, and I even cited it down here at the bottom. So I just got this off the internet. Basically, if you're taking a limit, okay, and I encourage you to read through this, but if you're taking a limit, and you direct substitute and end up with 0 over 0, that is what's called an indeterminate form, okay? If you get 0 over 0, you can't determine anything from that. And if you end up with this type of indeterminate form, 0 over 0, what L'Hopital's rule says is that you can do this. Okay, so the limit as x approaches a of f of x over g of x. Okay, and if you read above, I believe it says, I guess the derivatives have to be continuous at the value that we're approaching. Okay, but if you're trying to evaluate a limit like this, and if you direct substitute, you end up with 0 over 0, then what you can do instead is you can take the derivatives of the numerator and denominator and evaluate the limit that way. When I do the example, guys, I'm not going to exactly do it the way that it's written here, but it'll be similar. I'll show it to you. Actually, let me stop even referring to this page and just do the examples, and then after that I encourage you to look back at this because it'll make more sense then. Now down here, guys, for the second thing that talks about L'Hopital's rule, infinity over infinity is another indeterminate form. Okay, now, and then when you get into college, you might see these other types of indeterminate forms. 0 times infinity, 1 to the infinity, infinity to the 0. These can also be treated with L'Hopital's rule, but we're not going to do that for AP Calc. So let's just write ourselves a note right here. And sometimes it's spelled like L'Hospital, but they're not spelling it like that now. So I'll just say L'Hopital's rule when you get 0 over 0 or infinity over infinity when evaluating a limit. Okay, so please write that down for yourself. Okay, that's the big idea right there, guys. Okay, and I'm about to show you how to use it. All right, so flipping over, alrighty. So we're gonna do 2 examples. Okay, and guys, the way that I do these is very important. I learned at the workshop I went to over the summer that you can't just apply L'Hopital's rule. You actually have to be very clear to your reader about why you're able to apply it. So please copy this down verbatim, and also when you do your homework problem, which is only one problem, do it just like we are about to. Okay, so I'm evaluating a limit. The limit as x approaches 0 of this function here. The first thing you try when you're doing a limit is direct substitution. So if I direct substituted, I would end up with e to the 0 minus e to the 0 over 0. Now already I've got a problem because I know I've got 0 in the denominator, and so I'm not going to be able to even use direct substitution. But the reason why I'm doing this is because maybe I'll end up with an indeterminate form, 0 over 0 or infinity over infinity, in which case I'll be able to apply L'Hopital's rule. Well, this is 1, that's 1. 1 minus 1 is 0, so I end up with 0 over 0, which is actually good news. All right, so let me say this. Okay, so let me stop right there, and then I'm going to say it like this. I'm going to say to my reader, 0 over 0 is an indeterminate form. And then I'm going to say, therefore, by L'Hopital's, that's just named after the guy who discovered this. Therefore, by L'Hopital's rule, comma, I think. Therefore, by L'Hopital's rule, and guys, this is not optional, okay, what I just wrote down. This is actually, like, if you're doing this on the AP exam, you know, and you're on a free response section and you're applying L'Hopital's rule, they want to hear that you know, all right, this is telling our reader why we can use it. And then I'm telling my reader like that I'm using it. And so, therefore, by L'Hopital's rule, now I'm going to take the limit again. I'm just going to rewrite it. Therefore, the limit as x approaches 0 of e to the x minus e to the negative x all over x. Guys, L'Hopital's rule says that this limit is equal to this limit, e to the x minus e to the negative x, hi Loz, my sister just walked in, over that. So if you end up with 0 over 0, when you're taking, you know, evaluating a limit, then you can evaluate the same limit by, you know, still doing the limit, but taking the derivatives of the numerator and the denominator. Okay, so let's see what happens. So this is equal to the limit as x approaches 0. The derivative of e to the x is e to the x. I'm just going to take this derivative term by term. Okay, and then that's minus the derivative of e to the negative x is negative e to the negative x. So that's going to be, I'm going to be subtracting a negative, so I'm just going to go plus right away. E to the negative x all over the derivative of x is 1. Wonderful. Okay, so now guys, I'll bring the equal sign down there. Now we can direct substitute because it's not going to give us a 0 in the denominator. So this is equal to e to the 0 plus e to the 0. Both of those are 1. 1 plus 1 is 2. Okay, so that's how you use L'Hopital's rule. First, you direct substitute. If you end up with 0 over 0, or in the next example we're going to see infinity over infinity, then you just explain to your reader, this, you know, what you ended up with is an indeterminate form. Therefore, by L'Hopital's rule, the limit of that function is equal to the limit of the function with the derivatives of the numerator and denominator taken. And then you just go through that. Okay, now the next example here, example number 2. I want to go through this example, guys, but I'm going to be honest from the start that the end behavior model is way more efficient than L'Hopital's rule when you're working with a polynomial over a polynomial. Okay, this is still a valid exercise, but we've done things like this before, guys. If x is approaching positive or negative infinity, and you just have, you know, a polynomial over a polynomial, the end behavior model says that this function is going to behave way out at huge x values. This function is going to behave the same as 2x squared over x to the third. That would be the end behavior model. But let's not use that here because we want practice with L'Hopital's rule. Okay, but just to be clear, I would use the end behavior model if this showed up on a test or a quiz because it's way more efficient. Okay, so if I plug infinity, I can't plug infinity in, but if I imagine huge x values, this numerator is getting huge, so that's approaching infinity. The denominator also getting huge. All right, so I've got infinity over infinity, which is another of the indeterminate forms. that we can apply L'Hopital's rule when we have it. Okay. So I'm going to say to my reader, just like before, I'll say infinity over infinity is an indeterminate form. Therefore, by L'Hopital's rule, okay, and then I'm going to bring down this limit, the limit as x approaches infinity of 2x squared minus 5x over x to the third minus x plus 10 equals the limit as x approaches infinity, and then you just take the derivative of the numerator over the derivative of the denominator. Now, mind you, that is not the derivative of this function. You'd need quotient rule to find the derivative of the function. But you just take the derivative of the numerator over the derivative of the denominator. So this is 4x minus 5 over 3x squared minus 1. Well, guys, the beautiful thing about L'Hopital's rule is that you can keep going. So you can take the derivative as many times as you need to, as long as you keep getting indeterminate forms. So this here, guys, this would give us infinity over infinity again. So I'm going to apply L'Hopital's rule again. So by L'Hopital's rule, this is equal to the limit as x approaches infinity. Derivative of the numerator is 4. The derivative of the denominator is 6x. Okay, now this is something that we can get a handle on. As x is getting huge and huge and huge, so imagine, 6 times 10, 6 times 100, 6 times 1,000, 6 times a million. This function is getting smaller and smaller and smaller, closer and closer and closer to 0. Okay? Yep, so there's that, guys. Now, okay, so what I would like you to do, I think that you should write this down. I already wrote it ahead of time to save time, but I think right maybe down here, you should write yourself a note, and here it is. So if you want, pause the recording and write this down. Note, for infinity over infinity from a polynomial over a polynomial, just like this example, the end behavior model is much more efficient. Okay, so I would recommend that in the future. In the future, whenever I give you a problem like this, where you end up with infinity over infinity, I'll try to make it something where they're not polynomials, so that using L'Hopital's rule is more of a necessity. Okay, guys, so that's the first video of the third unit, and tonight's homework is just one example or one problem, and it's page 3, number 6, and I am going to start quizzing again. Okay, so tomorrow there will be a quiz at the beginning of class that is very similar to this problem that I'm asking you to do. All right, so try your hardest. If you have questions before the quiz, of course I will take them. And have a great night, guys. Bye-bye.